let's look at the fundamental theorem of calculus. This theorem relates differentiation and integration. So more simply, it tells us that slopes are related to areas, or equivalently, areas are related to slopes. So let's go ahead and we'll see why that is the case. So let's start off with this simple function, f of x equals ax. So we've seen this function whenever we looked at the equations of straight lines. The value of a gives us the gradient. We could replace the a with an m and it would be more familiar to us possibly. We would have f of x equals mx. So as we change this value a, it changes the steepness of the line. It changes the gradient. So let's put it back to 1. Now what we want to do is we want to differentiate this function. So we want to create a new function which tells us the gradient of this function. So we can see really what that's going to be at the moment. If the gradient of this function here is 1, so the rise divided by the run is 1 divided by 1, so the gradient is 1. It means whenever we differentiate it, we'll simply have a function here that runs along parallel to the x-axis at height 1. So let me go ahead and I'll put that in. So this is our function here, f of x equals ax, and whenever we differentiate it, we get this function here, which is simply the function y equals 1. And you can see why that works. In this function here, y equals 1, the height of it is 1 irrespective of where you are on the x-axis. So when I'm at 4 the height is 1, when I'm at 3 the height is 1, when I'm at minus 2 the height is 1. Because that height 1 represents the gradient of this line. And this line is always gradient 1, it never gets any steeper. So the height of this line here just tells me the gradient of this line. So that's us simply doing our differentiation. So we know that this differentiated function tells us something about the original function. The differentiated function tells us the gradient of the original function. But the secret here about the fundamental theorem of calculus is that this function here, the original function, also tells us something about the differentiated function. And that's what we're going to go and have a look at now. So what does this original function here tell us about the differentiated function? Well, let's see if we can work out just looking at it graphically. Let's look at the area of this function here between points 1 and 3. So between points 1 and 3 we can see the area is, well, you've got one block there, so that area is 1. You've got another block there, so that's the area of 1. So the total area between 1 and 3 under this function here is just that block plus that block, which is 2. But now we'll look at the value of this original function at that point 3. Well, the value of that original function at point 3 is 3. And the value of the original function at point 1 is 1. So 3 minus 1, which is this height here, is 2. But that value 2 is the same as the area here, which is 2. So really what we're saying here is the difference in height of the original function between these 2 points 3 and 1 is the same as the area of this new function between points 3 and 1. So now possibly difficult to see if you haven't seen it before. What we'll do is we'll look at another example that will show you this fundamental theorem of calculus. But in essence, the fundamental theorem of calculus relates gradients to areas. So we have the same line, f of x equals ax, where a equals 1, so that's just a line y equals x. We've differentiated it to get this line here, which is y equals 1. We're looking at the area under this curve y equals 1 from 3 to 1, and we've just drawn these lines in. So this is the area here, which is 1 unit plus another unit, so that's 2 units. So this area here is the same as the height here. And that height here is given by the value of this original function at 3 minus the value of the original function at 1. So really what we're saying, and in essence, the fundamental theorem of calculus is telling us that this height here is the same as this area here. So let's try a different line. Let's say the original line had the value a equals 2. So this is the line y equals 2x. Whenever we differentiate that, we get this line here, which is the line y equals 2. So let's look at the area from 1 to 3 under this function here, y equals 2. Well, that area is simply going to be 1, 2, 3, 4, so we've got 4 boxes, so that area is 4. Now if this is correct, then that area 4 must be the same as the value of the function, original function here, at 3, which is 6, minus the original value of the function at 1, which is 2. So it's going to be 6 minus 2, which is 4. Again, we're saying that this height here is the same as this area here. So if you look along the left hand side here, you can see here that I've written out what is really at the fundamental theorem of calculus. We have the area of this function here, which is given by the integral from 1 to 3 of a by dx, which is equal to a value of 4. So the area under this is 4, and that's the same as the height of the original function from points 3 to points 1. So we're looking at the f of 3, which is 6, minus the f of 1, which is 2, which is 4. And if we were to change these values, you'll see that those values are indeed the same in each case. So there it's 9.4 and 9.4. It's 5.2 and 5.2. But that's straight lines. What about curves? So let's do the same thing, but we'll use a different function. So the original function here is in red, and that is the function y equals x squared. And we know that whenever we differentiate y equals x squared, we get y equals 2x. So this other line here is the differentiated function. So we know from differentiation that this line here, it tells us something about the original curve. The thing it tells us about the original curve is the gradient at each point. So each height on this line here represents the gradient of the same x point on this curve. But we also know now that this original curve here also tells us something about this line. It tells us the area underneath the line. And we know that the area underneath the line is the value of this function here at this end point of the area. So if we go to the end point of the area here, it's going to be 0.3, so between 1 and 3. So if I go to 3 and I go up to this function here and cut across, you'll see it gives you a value of 9. And also if I would go to the point 1 here, which is the beginning of this area, and I go up to this curve here, it goes across and it goes to a point 1. So I know that the 9 minus the 1 is a value of 8, and I know that that height there is the same as this area here. So in fact what we've done is we've actually looked and compared them. So I've done the integration here of this function and I've found the area, and the area you see here is a value of 8, and that is equal to the value of the original function at those endpoints 3 and 1, and when we subtract those off we get the value of 8. So we can see here that the difference in heights here tells us the areas between those points. So again, this is the fundamental theorem of calculus. It relates differentiation and integration, and it relates them in the form of gradients and areas.